Okay, welcome back. We were talking about kernels and inner products. So we said that one of the ways to work with support vector machines to take care of the nonlinearities that exist in your model is to use something called support vector classifiers that is represented in inner products. And here we have an inner product function. We can say that in order to find the support vector classifier, the line that we were looking after, we can focus on the inner product. We focus on a function that is a function of inner products for every point x. For every point x, this function is a function of beta 0, which is a constant. Some alpha i's that needed to be estimated, plus the inner products of that point and all other points in our space. And these points, we have n of these points. So at the end, we need to estimate n parameters, alpha 1 through alpha n, and beta 0. So in order to do that, we can mathematically show that we need to estimate all inner products of all points, which are 2n, because we had n observations. If you want to estimate, if you want to have inner products of all points, you will have 2 out of n options. So that's why you have to estimate everything that you have. And once you do that, you get an easy way to find alphas, which is slightly beyond our scope of our lecture. But what I want to mention is that we are going to find that only the alphas that are in our margin. Remember when we had a classifier, we had margins around it. So what we can learn from it is only the alphas pertain to the points that are inside the margins would have non-zero values. Everything else will have zero values. So at the end, most of these alphas become zero. Only the support set, means the ones that are within our margins, will have non-zero values. Something wonderful about using inner products is that you can show them with something called kernels. So if you have nonlinear shapes, instead of adding more and more and more variables and estimating more and more coefficients, something that can be do is using kernels. For example, it's easy to show that polynomial degree d can be shown by a simple kernel like this to the power of d. For instance, polynomial of degree 2 is just 1 plus the inner product of the points to the power of 2. So instead of writing it as beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x1 x2 plus beta 4 x4 x1 2 plus beta 5 x2 2, we can write it as 1 plus summation of all inner products to the power of d. D here is 2. So for polynomial degree d, let's say d more than 5 or 6, we'll have very long expressions and very hard computations. But by using kernels, we will have an easier life. Then we will need to use these kernels and a function form that we see here. We already saw a simple inner product of the models we had in previous slide. Here, by using kernels of any degree, we just need to find again alpha i's. So we will be left with only the points that are within our support set. Everything else will be zero. So we will have a way easier computational time. So when we found the estimates of beta 0 and these alpha i's, we will have nonlinear boundaries or support set that will categorize our our subspaces. For and instead of kernel, we can also use another types of kernel. This is called kernel of radial kernel, which is defined this way. It looks like the Gaussian distribution function, density function, and this is actually kernel is relative to polynomial degree n. Gamma here is actually one of I think it's 2 times the standard deviation. Yeah, I think gamma is 2 times the standard deviation, so gamma is a positive number here. So we can, if we define kernel this way, we get very flexible functions. And again, no matter how you define your kernel, you will be left with estimating beta 0 and alpha i's, and each point that is in support vector or in the support boundary will have non-zero values. Everything else has 0 values, and this is the result of using this kernel with this shape with KNN. I'm sorry, with radial kernel. And as we can see, it did a pretty good job in summarizing our space into different categories. This is the boundary it gets, and these are the support vectors that we see. It characterized most of our categories correctly. So no matter what dimension we have here is actually dimension infinity with this shape, which we can only imagine. We cannot do anything about that. We can only imagine it. Even with that, we don't face that much computational. And that's the beauty of using kernels instead of inner products. We can use it for even the cases that we don't have any idea what it is. And here we have some representation of using support vector machine. Oh, by the way, sorry, before I come here, I have to say this gamma is a tuning parameter. We should tune it by checking different values for it. So it's not something we know in advance. That is something we should play around with to get the best possible result, like the one we see here. So here in this shape, I have to refer you to ROC. When we were talking about linear discriminant analysis and categorical variables, I introduced ROCs to you, and I told you that we are comparing false positive rate versus true positive rate, and ideally we want to be closer to here. So the best model is the one that has the closest ROC curve to this part. So this is these values are came from different values of gamma when it was tuned for different models, and the other different tuning parameters. So we get this beautiful ROC curve. So we want to be close to this as much as possible. And so this is for our test data. So this is for our training data on the heart. I think I was on heart. Yeah, that is predicting heart failure based on different different quantities we had in for some male South African males. So as you can see, if we look at the training data, what we see is that support vector machine with gamma 0.1 and also the kernel that we introduced, radius kernel, does better than support vector classifier, the simple support classifier in training set. And as we can see, the LDA and support vector classifiers are doing almost the same job. But that's just for our training set. But if we just look at the test set, we see a different story. We see that the blue curve does way worse than not way worse, but relatively worse than any other gammas that we've chosen. So it is suggesting that when lambda is small, delta is small, Is it delta or gamma? This is not, it's delta. So when delta is small, when delta is low, we have more flexibility. That means more variance. More variance tends to have less bias, and that means we went after individual observations. So that's a very good chance that we overfit here, because we did phenomenally well on our training data, but when it came to test data, we didn't do well. So in your test data, you will see that perhaps FCM with 10 to the power of negative 3 does the best. So we should always rely on test data instead of training one. And as we can see, support vector classifiers and LA does almost the same job, but radial kernel with delta 10 to the power of negative 3 does pretty good job, better than everybody else. So remember, we should always rely on your test data. Do not be fooled by, we should not be fooled by the information we get on our training data. So another question that we should answer is, what should we do if we have more than 2 classes? We just focused on the case that we have 1 class. What are the solutions if we have more than 2 classes? Let's say you want to see if you are a risky person, medium risk person, or low person. These are 3 classes. How can we do that? How can we manage to do that? The answer is usually there are 2 ways to deal with it. The first one is called one versus all, OVA, one versus all. So that means for every class, so let's say we have 5 classes. We have 5 classes. Then let's say this is 1, 2, 3, 4, and 5. We consider everything 2 by 2. This one with this one, this one with this one, this one with this one. And as you can see, there are a lot of different versions we can do it. Actually, if we have 5 categories and we want to do it 2 by 2, then we will end up with 5 factorial divided by 3 factorial times 2 factorial. So we will be left with 10 2 by 2 comparison. So we compare them 2 by 2, and each time we record who is the winner. So for every point, let's say we have 2-dimensional feature space, and let's say we want focusing on this point, this very point. For every point, we compare 2 classes and see which class we predict it belongs to. Let's say for 4 of we find that in 4 of the cases it belongs to class 1, 2 of the cases belongs to class 2, 2 of the cases belongs to class 3. So our prediction will be that it belongs to class 4. So that is called one versus all prediction. Another way to do that is we do it in this fashion, and actually this is more accurate. We just look at all classic 2 by 2 classifiers, and we see which one creates the largest deviation. So that means for which class the amount of our function is more positive, is largest on that point. Is it our, let's say, our f hat 1 x star is, let's say, 2, f hat 2x star is 3, and so on and so forth. The one that has the largest belongingness to the category will be chosen. I think that is more apparent than the one that I explained. And the next one is 1 versus 1. Actually, the one that I explained earlier was 1 versus all. So that is 1 versus all. 1 versus 1. In 1 versus 1, you're just comparing it 2 by 2, and you choose the one that wins the best. In 1 versus all, what you do is that you just find the different classifiers, and for each classifier, you see how much is the deviation of your point from all the classifiers. The one creates the largest deviation is the category you assign it to. Okay, remember when you would put that in your classifiers, it showed you different level of propensity that it belongs to. So that's how you do it. In 1 over versus 1 instead of 1 versus all, you do it 2 by 2. You have 2k positive classifiers, and you will see how many is won by classifier. For example, you see 3 of the 5 cases class 1 win, 1 case class 2 win, and so on and so forth. You assign it to class 1. So which one should we choose? If k is not too large, use OVO. So the reason I somehow missed the point in the beginning, the information I shared was somehow I jumped ahead, is that because most of the time you want to use 1 versus over. That's more accurate than this one. So if you can manage these many comparisons, use 1 versus 1, and that can happen when k is not too large. That's the case that you can compare them. If you have millions of categories, you cannot do it because you would need billions of, or maybe trillions of different modifications. Okay, so now the last question is, the last thing I want to discuss is, what is the distinction or closeness of support vector machines versus logistic regression? It turns out logistic regression and support vector machines can be translated to each other roughly, and that's by adding a lasso term to logistic to your support vector classifier. And so basically, these two things can be translated to each other if you add a lasso term to logistic regression, likelihood function of logistic regression. They would be almost similar. So the results they show you would be most of the cases the same or very close. So here we have some questions to consider. The first one is, when should we use support vector machines when we can use logistic regression or linear discriminant analysis? If your classes are nearly separatable, support vector machine does a better job all the time. So in comparison with support vector and logistic regression, support vector machine does a better job when your classes are better separatable. So in this case, you should use support vector machine. And LDA had the same characteristic, as you can remember. When not, linear regression with ridge penalty and support vector machines are very similar. So support vector machine always does a relatively good job. If you want to estimate probabilities and have some interpretability, you see how odds are being changed with some variables, and use logistic regression, because support vector machines are not built for interpretation. For nonlinear boundaries, support vector machines with high degrees of kernel are very popular. So we can use these kernels for logistic regression and linear discriminant analysis functions, but the computational part will be very expensive. So I would say if you have very highly nonlinear boundaries, then support vector machines with kernels does very good job, so specifically radial kernels. So that was our course about support vector machines. You will have a video on how to use R to work with support vector machine later. Thank you and bye.